Hello, students. Today is the first class of the session of S block elements. So I have divided this chapter between two segments. The first one will involve the alkali metals, and the second one will involve the alkaline earth metals. So we shall start with the a preliminary introduction of the S block elements. So S block elements, like are the group one elements in the periodic table. So in the group one, we have this lithium, sodium, potassium, rubidium, cesium, and francium. These elements are from up to down. In the group two, there are also S block elements, and they are collectively known as alkaline earth elements. So these are beryllium, magnesium, calcium, strontium, and barium. So now, for the group one elements, you can see they are popularly or collectively known as the alkali metals because their hydroxides are strongly alkaline in nature. These hydroxides might have encountered in the laboratory also, like sodium hydroxide or potassium hydroxide. These molecules are actually well-known alkalis that are used in the laboratories. And in the group two elements, their oxides and hydroxides are also alkaline in nature. But these metal oxides like calcium oxide or strontium oxide or magnesium oxide, these are found in the Earth's crust. That's why they are collectively known as these alkaline earth metals. Now, their general electronic configurations are as follows. For group 1 elements, that is the alkali metals or is group 1 or of the S block elements are noble gas NS1. This is the general electronic configuration of the group 1 elements. And for group 2, this is noble gas and followed by NS2. Now, these alkali metals have only one electrons in the valence shell, but the alkaline earth elements, that is the beryllium, magnesium, or the group 2 elements, have two valence electrons in the valence shell. Now, among all these elements, if we consider only group 1, lithium is the one element that shows some properties that are not shown by the other elements of the same group. So I want to state the fact like the sodium, potassium, rubidium, cesium, or francium. So some of the properties that are not shown by the lithium, and lithium shows some of the properties that are not shown by sodium, potassium, rubidium, cesium, or francium. The same thing goes for beryllium also. So beryllium shows some of the properties that are not shown by the other elements of the same group, like magnesium, calcium, strontium, barium, and radium. So lithium and beryllium both possess some anomalous properties that actually keeps them or holds them different from the other elements of the same group. Among all these elements from group 1, sodium and potassium, Na and K, are the two elements that are present in our biological fluids in a very large proportion. And the same goes with magnesium and calcium. You know that magnesium is present in chlorophyll, and this calcium is one of the main component for our bones and teeth and etc. So sodium and potassium among this is the group 1 elements, and magnesium and calcium are from the group 2 elements. These are the elements that are present in some large proportion in our biological fluid system. So now we'll go to the next slide. And before going to the next slide, we'll now discuss something here, that is the diagonal relationship here. So we will discuss this diagonal relationship later in detail. Lithium and magnesium show some properties similar to one another. And also this holds for beryllium and aluminium. So lithium and magnesium are diagonal elements. You can have a look in this picture here. Like lithium and magnesium are diagonal in the periodic table. That is cross to one another. So that's why this is called a diagonal relationship. So these diagonal elements have some properties similar to one another. And this also holds for beryllium and aluminium. So aluminium lies right here in the periodic table. It is a group 13 element. That's why it is not shown here. But if you have a look in the large periodic, actual periodic table, you will see aluminium and beryllium are also diagonal to one another. That's why they also possess some properties similar to one another. So lithium and magnesium and beryllium and aluminium, these two couple of elements actually. This element duo are called the diagonal relationship element. They possess some diagonal relationship between one another. We will discuss about this in detail in the later slides. So in this next slide, we will encounter some of the atomic and the physical properties of the alkali metals. You know, these properties are actually shown in the left hand side, and the diagonal elements are actually shown here. The lithium, sodium, potassium, rubidium, cesium, and francium. The properties are ionization enthalpy, hydration enthalpy. Both are depicted in kilojoule per mole because these are the energy terms. The metallic radius are the next ones, or the ionic radius. The metallic radius means the element in their free state or their zero oxidation state. The ionic radius means the elements are in their usual oxidation state. In this case, all the alkali metals have their usual oxidation state +1. That's why when we will discuss about this ionic radius, all the metals will be in their +1 oxidation state. So lithium plus, sodium plus, Ka plus, and so on. Also, the melting point or the boiling points in Kelvin, the density in gram per ml, and the last topic is the standard electrode potential for this M plus M duo. So we will discuss all the things one by one. So firstly, we will catch this ionization enthalpy. So you might have read about ionization enthalpy. Ionization enthalpy is nothing but the energy that is required to pull out the valence shell electron from the atom in the gaseous state. Now, when we are talking about this lithium or sodium or potassium or rubidium, cesium or francium, you see there is a decreasing trend of ionization enthalpy from lithium to francium. Lithium possesses 520, sodium possesses 496, potassium possesses 419, rubidium 403. So gradually it's decreasing, the ionization enthalpy value. Now, the hydration enthalpy, when we will discuss, you can also see a decreasing trend here. The lithium is 506, sodium is 406, potassium is 330, and so on. So there is a decreasing trend in the hydration enthalpy also. So why the ionization enthalpy decreases from lithium to francium? So from lithium, we can see the size of lithium is the smallest, because you know when we are going down the group, lithium is the smallest one and the francium is the largest one. So block elements, and the S block elements, we have divided the chapter in two segments. The first one is the alkali metals, that's the group 1 elements, and the second one is the alkaline earth elements, that is the group 2 elements. So in the first session, we will discuss about the alkali metals. So before going to the alkali metals, this is a preliminary introduction of the elements. In the group 1, the elements are lithium, sodium, potassium, rubidium, cesium, and francium. So this is the down the group trend. From lithium to francium, the size actually increases. So in any group in the periodic table, the size from the top to bottom, the atomic size or the ionic radii of the elements increases. The group 2 elements are beryllium, magnesium, calcium, strontium, barium, and radium. So here also from beryllium to radium, the size actually increases. So the first, that is the group 1 elements, that is the alkali metals, they are collectively known as alkali metals because their hydroxides are strongly alkaline in nature. You might have encountered the sodium hydroxide or potassium hydroxide in the chemistry laboratory. This NaOH or KOH, these are the mostly used alkali and they are strongly alkaline in nature. That's why all the elements of this group 1 are collectively known as alkali metals. In the group 2, we have from beryllium to radium. These oxides or hydroxides are also alkaline in nature, but their metal oxides are found in the Earth's crust. Crust means in the upper layer of the Earth that is actually covering the entire Earth. So this in the crust, this magnesium oxide or calcium oxide, beryllium oxide, these kinds of oxides are largely found. That's why these elements are collectively known as the alkaline earth metals because they are earth abundant, they are oxides. So none of these group 1 or group 2 elements are found in the nature in their free state. So in all the cases, we will find them as their halides or their oxides or their hydroxides, because all these elements are highly reactive in nature. Their general electronic configuration, is noble gas NS1 for the group 1 elements. And for group 2, the general electronic configuration is noble gas followed by NS2. So only one electron is in the valence shell of the group 1 elements, and there are 2 electrons in the valence shell of the group 2 elements. So lithium and beryllium are the 2 elements. They show some properties that are not shown by the other elements of the same group. What I want to say, like the lithium shows some of the properties that are not shown by sodium, potassium, rubidium, cesium, or francium. The same goes for beryllium, because beryllium shows some of the properties that are actually completely different from the magnesium, calcium, strontium, or so on. So these lithium and beryllium are the 2 elements that show some anomalous properties. That properties are not shown by the other elements of the same group. That's why they are put separate or distinct. They are distinct from the other elements of the same group. Among all these elements, the second and third, like sodium and potassium in case of group 1 and magnesium and calcium in case of group 2, are present in some large proportion in the biological fluid system. So in our body, these elements are found. You know about magnesium. Magnesium is one of the major components in chlorophyll. That is, chlorophyll is the pigment that is responsible for the absorption of sunlight by the plants. You might have known about all these things. And calcium, you all know, like, is one of the major component for the formation of bones, teeth, etc. Now, there is a separate thing that we will discuss later, but I have depicted this here. That is the diagonal relationship. Like lithium and magnesium, you see here, lithium and magnesium are diagonal to one another. In the periodic table, you will have a look, like lithium and magnesium are crossed to one another. That is diagonal. And beryllium is also having a diagonal relationship with the element that is here, that is aluminium. Since aluminium is a p block element, a group 13 element, that's why I have not shown it here. But beryllium is also diagonal to aluminium. And it has been found that lithium and magnesium possess some similar properties with one another. The same goes for beryllium and aluminium. Beryllium and aluminium also possess some properties that are actually quite similar to one another. That's why these 2 coupled duo, that is the element duo, lithium and magnesium and beryllium and aluminium, are the 2 elements that show this diagonal relationship. So we will discuss about this thing in detail in the later slides. So in this next slide, I have actually collected some atomic and physical properties of all the alkali metals. The properties are shown in the left-hand side. You can have a look at this. Is the ionization enthalpy, kilojoule per mole, hydration enthalpy, metallic radius, ionic radius, their melting or boiling point, their density, and the standard electron potential. And in the right-hand side, you see the elements are actually shown from lithium to francium. So we will catch one by one. First is the ionization enthalpy. So ionization enthalpy is nothing but the energy that is required to pull out the valence shell electron of a specific element in the gaseous state. So you see from lithium to francium, the ionization enthalpy decreases. So there is a decreasing trend from lithium to francium. So what is the reason? So lithium is the smallest in size. And that's why the energy required to pull out the last electron from the valence shell is actually highest in case of lithium. That is actually not in the case of francium, because francium is quite large in size, and that's why the energy required to pull out the valence shell electron is quite less. So we can discuss this example by the effect of some another example. So you see, whenever something is small in size, so the nucleus will show some greater power on the valence shell electron in case of lithium, because the nuclear charge is same from lithium to francium. In all the cases, the nuclear charge is actually +1. But you see, when the size will be small, then the nucleus, so the outer valence electron will be close in proximity with the nucleus. That's why it will be more tightly bound to the nucleus in case of lithium, and it will be loosely bound in case of francium, because the atomic size of francium is quite high. So the ionic size of francium is also high. So then the valence electron will be too far from the nucleus. That's why the power of nucleus on the valence electron will be least in case of francium, but in case of lithium it will be highest, because lithium is smallest in size. That's why the nucleus will keep the electron, the valence electron of lithium, most tightly bound. But in case of francium, the valence electron will be loosely held or loosely bound. So whenever it is loosely bound, so the less energy will be required to pull it out. But when the electron is tightly bound to the nucleus, so we will require some more amount of energy to pull out the valence electron. That's why the ionization enthalpy of lithium is the highest, and in case of francium, it will be the lowest one. So this is the reason, this is how we can explain like why lithium, in case of lithium, the ionization enthalpy is the highest, and why in case of francium, it is the lowest. Now we will go to the second one, that is the hydration enthalpy. Now hydration enthalpy means the solubility of the corresponding cation. So you see here also the size actually plays the predominant role. The size also plays the predominant role. Here also you can see from lithium to francium, the amount, the hydration enthalpy value decreases. You can see a decreasing trend. This is 506, then this is 406, is then 330, then 310, this is 276, and so on. Now, how we will explain the decreasing trend of the hydration enthalpy. Now, the charge of lithium is the small, is in all the alkali metals is just the same. That is a +1. We have told about it. But the radius or the size of the atom increases from lithium to francium. Now I will introduce a term here that is nothing but the ionic potential. So ionic potential is nothing but the charge by radius ratio of a specific cation. Now, in all these cases, the charge is fixed, so we will not talk about it because it is same for all the elements. But the radius is also changing from lithium to francium. So we will talk about radius. Now, the ionic potential value is now inversely proportional to the radius of the cation, because ionic potential is charge divided by radius. So more the radius will be, the less will be the ionic potential, or the less the radius will be, the more will be the ionic potential. So you see, since lithium is the smallest one, its radius is the smallest one, so its ionic potential will be the largest one or the highest one. But in case of francium, the ionic potential, or cesium, the ionic potential value will be the lowest one, because the size of cesium is the highest one. That's why the ionic potential value of lithium plus cation is much more than that of the cesium. So the more the ionic potential will be, the more will be the hydration enthalpy of the corresponding cation. That's why the lithium plus is having the hydration enthalpy highest, but in case of cesium, it is the lowest. So whenever the ionization enthalpy is required, so we will talk about this radius. In case of hydration enthalpy also, we will talk about the ionic potential. Now the ionic potential is inversely proportional to the radius. So the less the radius will be, the more will be the hydration enthalpy. And the more will be the radius, the less will be the hydration enthalpy. Now I have already talked about this metallic or the ionic radius here. You can see the ionic radius is having an upward trend here from lithium to francium. Is 76, is 102, it is 138. That's why it is gradually increasing. So I have already told about why it is so, because in down the group, when we go down the group, the principal quantum number, that is the n, will increase. That's why the atomic or the ionic size will increase. So you see the ionic radii also of the metallic radii are increasing here down the group, like from lithium to francium. In case of melting point or the boiling point, that you can see a decreasing trend here, because in case of the smallest element, the melting point will be the highest, because in case of the boiling point will also be the highest, because in this case, whenever the atom or the ion is smaller in size, in that case, the metallic bonding becomes stronger because small things will interact with small atoms more than the larger ones. That's why the melting point or the boiling point, both in case of lithium are the highest and both in case of cesium is the lowest. When we'll go to the standard electrode potential, we see that is in case of lithium, the value is the negative value is the highest one. You might have thought about it like it is minus 3.04, that is the lowest, but it is not the case, because the minus sign is not actually will be taken into account, but the mod value of the standard electrode potential will be depicted here. So lithium is having the highest negative value among all the alkali metals. So it is the strongest reducing agent. You see here in case of potassium, rubidium or cesium, the values are actually comparable to one another. So they are approximately the same. But in case of sodium, you see the value is the lowest one. Sodium is the least powerful reducing agent among all the alkali metals. And lithium is the strongest reducing agent among all the alkali metals. So in the next slide, some chemical properties are actually collected here. So we will discuss all about it one by one. First one is the reactivity towards air. You see all the elements are actually here shown. When they are reacted in air, the aerial oxygen reacts with all the elements, all the alkali metals in some different proportions. You see lithium reacts with dioxygen to form lithium monoxide. Sodium reacts with dioxygen to form sodium peroxide. And all the other elements, like the potassium or rubidium or cesium, that is the other alkali metals, the heavy alkali metals, they form superoxide. So O2 minus is nothing but oxide, O2 2 minus is nothing but peroxide, and O2 single minus, that is the superoxide. So the alkali metals actually react with oxygen in some different proportions. Depending on the metal, their reactivity pattern changes. So how they will react or what is the product, in the later slide I will discuss how you can remember like how this which element reacts with oxygen to produce which kind of oxide. So lithium is the only element in the alkali metals among all the alkali metals that react with molecular dinitrogen to produce this lithium nitride, that is Li3N. So I have already told you that lithium is the one element that shows some anomalous properties. These properties are not shown by the other elements of the same group. This is one of the examples. Like lithium is the only element among all the alkali metals that reacts with molecular dinitrogen in the air to produce this lithium nitride. None of the other alkali metals, that is sodium or potassium or rubidium or cesium, react with dinitrogen to produce this Na3N or K3N, such kind of molecules. Now the next one is the reactivity towards water. So all the alkali metals dissolves in water to produce the corresponding alkali, and molecular dihydrogen is released, where M is the alkali metal. This is the equation, 2M plus 2H2O producing 2M plus 2H minus, that is the alkali combo, and the molecular dihydrogen. Now although lithium possesses the most negative E0 value, in the last slide you might have encountered that like lithium is possessing some minus 3.04 voltage electrode potential value. So it should react with water more vigorously, but that is not the case. The sodium, which is having the least negative E0 value, that is minus 2.7, that actually reacts with water more vigorously. So that is an anomaly kind of thing. So we can address the thing by the reason, the high charge density and very high hydration energy of lithium plus. So you can see there is a metal plus cation, the lithium plus. So in the last slide, I have told you about the ionic potential. So ionic potential is nothing but the charge by radius ratio. So charge by radius ratio, we can depict in the form of charge density. So what amount, in the amount of smaller radius, if a same charge is accumulated, then charge density will be high. Since lithium, sodium, potassium, all the alkali metals are having the +1 charge, but the size of lithium is the smallest. So it has the highest charge density or the highest ionic potential. That's why it is having the highest hydrogen energy. That's why the hydrogen enthalpy of lithium plus cation is the highest one. So in the last slide, I have already discussed elaborately why lithium plus is having the highest ionic potential or the highest hydrogen energy or the hydrogen enthalpy, you can say. That's why the lithium to lithium plus reaction is less vigorous than the sodium to sodium plus reaction. Reactivity towards molecular dihydrogen. So all the alkali metals at some different temperatures react with molecular dihydrogen to produce the corresponding metal hydride. So 2M plus H2 will produce 2MH. So at very high temperatures also the reaction proceeds 673 to 1073 Kelvin. So reactivity towards halogens. Now these alkali metals react vigorously with halogens forming ionic halides. Now the ionic halides have some common abbreviation as MX. Now all the alkali metals react vigorously with halogens and the product is the MX. So 2M plus X2 will produce 2MX, just as the hydride in case of. Now in case of lithium iodide, it is the most covalent one in nature. Now, in this case also, you will have to remember about the concept of the ionic potential. So, ionic potential is one of the major concepts in the cases of alkali metals or alkaline earth metals that you have to remember. So, here a Fajan's rule comes into picture. Now, I have actually depicted here that Fajan's rule actually can help us in predicting the nature of compound, whether it is ionic or it is covalent in nature. Now, I have written here that lithium iodide is the most covalent compound in the one in nature. Now, how will address? What is the reason behind it? Or what do I mean by the most covalent one? Now, Fajan's rule depicts us when the cation is having the highest ionic potential, it will distort the electron cloud of the anion more. So when a cation is having the highest ionic potential, it is having the highest charge density. Because ionic potential is nothing but charge by radius ratio. So when the ionic potential will be high, the charge density will also be high. So when the cation is having the highest charge density, it will distort the electron cloud of the anion. So a cation will distort the electron cloud of the anion because anion's electrons are loosely bound in nature, but the cation's electrons are tightly bound in nature. So the cation will deform or distort the electron cloud of the anion. So when the anion's electron clouds will be distorted, then the electron cloud of the anion will be mixed with that of the cation. So whenever an electron cloud will be mixed between the cation and anion, a bit of covalency arises, because you know covalency is nothing but mixing of electrons or mixing of orbitals. So when a cation is having a high ionic potential, it will distort the electron cloud of the anion. And when it will distort the electron cloud of the anion, the mixing of electrons between the cation and anion will happen. So then a bit of covalency will arise in the compound. So you see the iodide, I minus. I minus is the softest one because I minus is the largest anion in the periodic table, because you can see at the halogens are naturally depicted as FClBrI. So from fluorine to iodine, the size actually increases. So the size of the iodide ion is the highest one. That's why it is kind of soft and polarizable. So its electron clouds can easily be distorted. And among all the alkali metals, you see lithium plus cation is having the highest charge density. So it will distort the electron cloud of the iodide anion more. So mixing of electrons will happen between the Li plus and the I minus anions. And that's why a bit of covalency will arise. That's why lithium iodide is the most covalent one in nature. So exactly opposite will happen in case of cesium fluoride, that is CSF. You see cesium plus cation is the largest one. That's why it is having the least charge density. So, and F minus is the one anion which is hard. It is small in nature. It is hard also in nature. And that's why the distortion of electron cloud of the F minus anion is practically impossible by the large CS plus cation. That's why F minus is less polarizable. So its electron cloud cannot be distorted by the CS plus cation. So cesium fluoride is the one compound that is least covalent in nature. So lithium iodide is the most covalent and cesium fluoride is the least covalent. So Fajan's rule can be used to predict the ionic or the covalent nature of the compounds. Now the next topic arises at the reducing property. So lithium being the most powerful, that is I already have depicted in the last slide, and sodium being the least powerful reducing agent. But how we can address this fact? Now the reduced power of the reduction potential, reducing agent, how good a compound is as a reducing agent or how poor, it is solely dependent upon the standard electrode potential, that is the E0 value. Now, a standard electrode potential is nothing but the combination of many factors. The factors are, first one is the sublimation enthalpy. The second one is the ionization enthalpy that I have discussed already. And the last one is the hydration enthalpy. Now, I have already told that the lithium plus is the smallest one. That's why it is having the highest charge density. It is having the highest ionic potential. That's why it is having the highest hydration enthalpy. So the hydration enthalpy is so large, so it outweighs the factor of the high ionization enthalpy and also the high sublimation enthalpy. So this hydration enthalpy value overcomes the high ionization enthalpy and the high sublimation enthalpy in case of lithium plus, because it is so small in nature. That's why it is having the highest hydration enthalpy. That's why the reducing power of lithium plus is the highest one. So since it is actually a combination of all the factors, so these are the actually experimentally obtained data. So experimentally it has been obtained, the summation value of sodium plus cation is the smallest among all the alkali metals. That's why Na is the least powerful reducing agent. The last topic is the solutions in liquid ammonia. It is quite interesting. So whenever you will dissolve an alkali metal in liquid ammonia, you will find some beautiful blue color in the solution. So whenever an M, that is the alkali metal, is dissolved in some moles of ammonia solvent, you see MNH3 whole X plus. So the metal will be ammoniated because ammonia is having a lone pair of electron on the nitrogen atom. So it will be coordinated to the alkali metal. So then MNH3 whole X plus is the one alkali cation, and the electrons then will be surrounded by the NH3 molecules and it will have a net negative charge. So you see from M we are having M plus ammoniated and electron minus, that is also ammoniated. So now this ammoniated electron is actually capable of absorbing the energy in the visible region of light. Now, whenever it is going down, it will be imparting the blue color to the solution. So whenever we will dissolve an alkali metal in liquid ammonia, the metals will be ammoniated and the electron will be free. Now the free electron is actually responsible or the culprit behind the beautiful blue color of alkali metal in ammonia solution. Now in the next slide, I will discuss about the diagonal relationship between lithium and magnesium in detail. So in the first slide, I have already told, like the later slide, I will discuss about this. Now you can see it is the atomic radii of lithium is 152 picometer. That is comparable with that of magnesium, that is 160 picometers. You also see the ionic radii of lithium is 76 picometer. In case of magnesium, it is 72 picometer. So you see the atomic or the ionic radii of lithium and magnesium are very much comparable to one another. So what is the reason behind it? For this, we should go to the first slide. So in the first slide, you see from lithium to beryllium, the size is actually decreasing. So you know about the periodic table. In a periodic table, when in a period we are going from left to right, the size actually decreases. So and in the group, in a period, when in a group from top to bottom, when you will go, the size will actually increase because the principal quantum number will increase. So you see from lithium to beryllium, the size actually decreases, and from beryllium to magnesium, it again increases. So suppose we are starting with 100 and we are getting decreased by 5, so it will be 95, and again we will be increasing by 6, so it will be 101. So from 100 we are going to 101. So you see there 6 things will be comparable, because from lithium to beryllium the size will decrease, and from beryllium to magnesium the size will increase. The same goes for the electronegativity also. From lithium to beryllium, the electronegativity increases, because in a period from left to right, the electronegativity increases. And in a group, when we will go from top to bottom, the electronegativity decreases. So from lithium to beryllium, electronegativity increases, and from beryllium to magnesium, electronegativity decreases. So by this decrease and increase will counteract with one another. So in what will be the case? The lithium and magnesium will have comparable atomic or ionic radii, comparable electronegativities. That's why they are possessing some properties that are chemically and physically very much comparable with one another. So this is the reason behind the diagonal relationship between lithium and magnesium. So these are the 5 factors which actually are points that show they are having some similar properties with one another. The first one is lithium and magnesium both are harder, and they're also lighter than the other elements of their respective groups. The second one is they react slowly with water, both of them from nitrides. The first one is lithium. Lithium reacts spontaneously in air to form lithium nitride. Magnesium is one of the very few elements that spontaneously react in air to produce this magnesium nitride, that is Mg3N2. Both of this lithium oxide and magnesium oxide, they don't combine with excess oxygen to give any superoxide. So in both the cases, they are stable in their oxide form. Lithium oxide is also stable in oxide form. Magnesium oxide is also stable in its oxide form. The carbonates of lithium and magnesium decompose are easily on heating to form the oxides and CO2. None of them form solid hydrogen carbonates. So you see, both the lithium and magnesium carbonate, Li2CO3 or MgCO3, they decompose easily on heating, and they form their corresponding oxides. Lithium carbonate forms lithium oxide, magnesium carbonate forms magnesium oxide, and both of them release CO2 easily if they are heated. But none of them forms this hydrogen carbonate or the bicarbonate. That's LiHCO3 is non-existent, and also MgHCO3 is non-existent. Both LiCl and MgCl2 are soluble in ethanol. So here also, in case of the Fajans rule comes into picture, Li plus or Mg2 plus are comparable to one another. That's why they are having some high ionic potential. That's why a bit of covalent in case of their halide salt. So LiCl and MgCl2 both are having some covalent character. That's why they are soluble in the organic solvent like ethanol. They are both deliquescent and crystallize from aqueous solution as hydrate. So in both the cases, lithium plus or Mg2 plus will catch water very, very soon. LiCl is very much deliquescent, or it is actually able to absorb water. So why is the reason? That's the reason behind the hydration enthalpy. So since they are having very high ionic potential, their hydration enthalpy is quite high. That's why they easily catch moisture from the air or the element or the ambience, and they form the hydrates. So LiCl will be formed as LiCl dot some XH2O. MgCl2 will be stable as MgCl2 dot 6H2O. That's why LiCl and MgCl2 salts are found as hydrates, or they crystallize as hydrates. So now when the chapter is actually, now I've depicted some of the major points of the chapter. Now we will go to some question and answer session. So firstly, which one of the following alkali metals is expected to melt above 30 degrees Celsius? The reason, the options are rubidium, sodium, potassium, and cesium. So the answer is cesium. So with increasing size down the group, the interaction decreases. So I have told about this earlier. Whenever a size is actually increasing down the group, so lithium is the top, so sodium, then potassium, then rubidium, and the cesium. So cesium is the largest alkali metal in the group 1 element. So whenever the size will increase, the interaction between the elements will decrease. That's why they will not form as remain as solids, but they will remain as liquid in the ambient temperature. That's why cesium, when it is put at only 30 degrees Celsius room temperature, it will melt, because the interaction between the cesium atoms is very less. You see that when the interaction is highest, it will form solid. When the interaction is bit lower, it will form liquid, and the interaction is very low, it will form gas. So these are the main physical states of matter that are actually concerned. Now, since in case of cesium, the atomic interaction is decreased because of the increasing size. That's why it is actually present in the atmosphere in ambient temperature as liquid. So the other liquids that are liquid metals that are present in our universe are mercury and gallium. So mercury also is a liquid metal, and gallium is also a liquid metal. So for your information, I will tell cesium is having a melting point of only 28.5 degrees Celsius. So above this temperature, it will melt. Now, what color does potassium impart when put to the flame test? So whenever an alkali metals are put to flames, it will produce some beautiful color. So you can read about it. What are the color that are produced by the other alkali metals? So you know about I have told about the general electronic configuration about the alkali metals. It is noble gas NS1. So alkali metals have only one valence electron in the valence shell. So whenever alkali metal will be put to flame, so it will catch energy from the flame, and the flame's energy will be enough to actually excite the valence shell electron, that is the one electron NS1. So S electrons will be excited. Now when the excited electron will come back to the ground state, it will emit in the visible region. That's why we will see some beautiful colors whenever we will excite a alkali metal when we will put to flame. So the violet color is generated whenever potassium is actually put to flame. So the color shown by potassium is violet. This crimson yellow color or the orange yellow color will be produced by sodium. In case of potassium, the color is violet. The next question we will discuss about it. Which among the following metal carbonates is thermally the most stable one? CH2CO3, Na2CO3, K2CO3 or Li2CO3. So 4 options are given, but the correct option is cesium carbonate, that is CH2CO3. So to explain the fact, we will have this popular equation, that is M2CO3, that is the common alkali metal carbonate, where M is the alkali metal. Whenever it is put to heat, this delta notion is actually used to denote the heat. It will produce either M2O, that is oxide, it will or produce M2O2, that is peroxide, or it will produce MO2, that is superoxide, and CO2 will be eliminated. So how we will discuss it? So this CO3 minus, that is the carbonate anion, is quite soft and large. So it is a large anion and it is soft in nature. Soft means the electrons are loosely bound, so it can be distorted quite easily. But in case of these, the oxides or the peroxides or the superoxide, you can see there is the O2 minus, only one atom, O2 minus, 2 atoms, and O2 minus, that is only 2 atoms. So these are actually small anions, and they are hard anions, because oxygen is very much electronegative in nature, but carbon is not as much as electronegative as oxygen is. So because of the presence of carbon and because of presence of the dinegative charge, carbonate anions are soft and large. But oxide or peroxide or superoxide, these anions are smaller and these are actually harder. So whenever an anion is soft and large in size, it is easily polarizable. That's why, so what do we mean to say? The electron clouds of the anion will be more easily distorted. That's why whenever we are having metal which is having a very high ionic potential, that is smaller in size, that is a hard cation we are having, that is suppose in case of lithium. So lithium will polarize the carbonate anion more than cesium because cesiums are larger in size. That's why in case of Li2CO3, Li plus cations, because they have some high ionic potential, they will distort the electron cloud of carbonate and they will form the corresponding oxide. In case of sodium also, since sodium is also having some high ionic potential, it will distort the electron cloud of carbonate and it will produce the corresponding M2O2, that is Na2O2, and CO2 will be liberated. But when the size will increase, as we saw for potassium or rubidium or cesium, you will see the the ionic potential value of the cation will decrease because the size increases. So then they won't be able to distort the electron cloud of the carbonate. So in those cases, the heat required will be more. So that's why in case of cesium carbonate, it is thermally more stable because more amount of energy is required to initiate the cesium carbonate to cesium oxide plus CO2 case. So you can say, like in case of M2CO3, whenever the cation is smaller in size, the large anion CO3 minus will not be stable. That's why they readily form the oxide. But whenever the cation size is quite large, so large cation, large anion combo will be the most favorable one. That's why they will be the most thermally stable compound. That's why cesium carbonate is the thermally most stable one and lithium carbonate is thermally the least stable one among all the alkali metal carbonates. The next question is the correct order of decreasing ionization enthalpy of alkali metals. So I have already discussed about this thing in detail in the previous slide, why or how we can determine that is the decreasing order of ionization enthalpy. That solely depends upon the size of the alkali metals. So the size actually decreases from cesium to lithium. Lithium is the smallest one. Lithium less than sodium, less than potassium, less than rubidium, less than cesium. The less will be the size, the more will be the amount of energy required to pull out the valential electron. So the more will be the ionization enthalpy. So lithium, having the smallest size, is having the highest ionization enthalpy. So the order will be lithium greater than sodium, greater than potassium, greater than rubidium. The next question is regarding the incorrect statement for the molecule CsI3. So first one, it contains Cs plus and I3 minus anions. It is a covalent molecule. It contains Cs plus, I minus, and lattice iodine molecule, that is I2. And the last question is option is it contains Cs3 plus and I minus anions. So here I will tell you a trick how we will answer the questions. So here the incorrect statements is actually required. So I have already told you that all the alkali metals will only show the +1 oxidation state. So the +1 oxidation state is exclusively and solely shown by all the alkali metals, whether it is lithium or sodium or any alkali metal. So whenever you see a cesium 3 plus is written here, that's why it will be false. Because I have already depicted or told you like cesium plus or lithium plus will be the only thing that is possible. Because after that, it will contain or it will comprise of the electron configuration of the noble gas. So it will not allow to pull out the electrons of the last of the noble gas configuration. So cesium plus is okay, but cesium 3 plus is inexistent. It's impossible to find a cesium 3 plus cation. So whenever it is written like it contains cesium 3 plus and I minus ions, so then this statement will be depicted as the false one. So the correct option is option D. It is an incorrect statement for the molecule of CsI3, that is it contains Cs3 plus and I minus anions. Next question is KO2, that is potassium superoxide, is used in oxygen cylinders in space and submarines. The reason is it absorbs CO2 and increases O2 content. It eliminates moisture. It produces ozone, that is O3, or it absorbs CO2. The correct option is option B, that is it eliminates moisture. For your reference, I have given the reaction. You see here potassium superoxide reacts with moisture or water to produce this alkali, that is potassium hydroxide. And this water is actually oxidized here to produce hydrogen peroxide, and also a O2 is liberated. So it is nothing but actually here O2 is liberated. So The correct option is it actually consumes the moisture, so it eliminates moisture and increases the oxygen content. Next question is state whether KO2, that is potassium superoxide, is diamagnetic or paramagnetic in nature. Now, whenever I will teach about the HOMO or the MO, this is a molecular orbital of the homonuclear diatomic molecule, I'll show you like how the molecular orbital is actually placed. So for this time being, I will tell you, like in case of O2 minus, there is a one unpaired electron in the pi star 2p molecular orbital of the O2 minus species. That's why a single electron is present there. So that's why KO2 is paramagnetic in nature, because O2 minus, that is the superoxide anion, is itself paramagnetic. K plus is not paramagnetic because K plus is having the electron configuration of noble gas, but O2 minus is paramagnetic in nature because it contains one unpaired electron in the 2p pi star MO. That's why KO2 as a molecule is paramagnetic in nature. Now, in this case, I'll discuss about the mnemonics and tricks, like what will be required to you. Like in this case, you can see first one is the ionization enthalpy. From lithium to cesium, you see the trend is decreasing. D stands for decreasing and I stands for increasing. Same goes for the hydrogen enthalpy also. From lithium to cesium, it is D. Same is also for melting point or boiling point in Kelvin. From lithium to cesium, it is decreasing. In case of density, that you do not have to remember that, but if you want to remember, that's why I have put down. You see, from lithium to sodium, it is I, so increasing. From sodium to potassium, it is D, that is decreasing. From potassium to cesium, it again increasing. So it is to be denoted as IDI. So alternatively, IDI. In case of standard electrode potential also, from lithium to sodium, it decreases, so it is D. And from sodium to cesium, it again increases. So it is Di. So whenever we will talk about the trend, you will remember about this in an alternative way. So it will be D, then it will be IDI. So IDI, it will be alternative. I for increasing, D for decreasing. And in case of standard electrode potential, it will be Di. So metallic or ionic radius, you will all know, it will be increasing from lithium to cesium. So that will be I. So here is one of the major tricks I have shown you, like how you will remember which element will produce which kind of oxide. So you see here lithium produces normal oxide, sodium produces peroxide, and the other elements produce superoxide. So now you can have a correlation between the element and the oxide. So lithium is the smallest one, so it forms oxide. Sodium is larger, that's why it forms peroxide. So per is actually comes in front of oxide. And in case of the other elements, that is potassium, rubidium or cesium, we are having a Su in front of per. So it will be superoxide. So you will remember by the thing, for the smallest one, sodium, it will be oxide, it will be 5 letters. In case of larger elements, that is sodium, it will be 8 letters. So peroxide. And in case of the more larger elements, that is potassium, rubidium, cesium, that are even larger, it will be superoxide. So sodium, so lithium, sodium, potassium, and here we have oxide, peroxide, superoxide. So whenever the size will increase, the name of the oxide will also increase. So this is how you can remember quite easily which element produces which kind of oxide. When the element is small, it will produce a small oxide. When the element is large, sodium, it will produce a larger oxide. So it will be peroxide. And when the elements are even larger, it will be superoxide. So that is one of the major trick that is actually will be helpful for you to remember how the alkali metals react with oxygen and produce which kind of oxides. So with this, I will draw the conclusion to the S block elements or the alkali metals. So in the next session, we will discuss about the alkaline earth metals or the group 2 elements. Thank you.